Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, St. Augustine.
I'm Philip Emeagwali. To invent is to see something that was previously unseen, and to see something that did not previously exist. I invented new computational mathematics that are important to my oil-producing country of birth, Nigeria, and that will enable the petroleum industry to use the massively parallel processing supercomputer to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I invented new computational mathematics because I asked important mathematical questions that are central to the toughest problems in computational physics. The research pure mathematician asks questions that are directly centered on mathematical knowledge itself. I am the research massively parallel processing computational mathematical physicist who asked mathematical questions that had corresponding physical answers. As a pure mathematician of the 1970s, I knew there are no easy quote-unquote new mathematics. Also, I knew that it is beyond the intellectual reach of somebody trained only in pure mathematics to possess a deep understanding of the 81 partial derivatives that represent the four physical forces that define the second law of motion of physics, and to as well understand that 36 partial derivative terms are missing in the mathematical physics textbooks on the multi-phase porous media flows, and missing since Darcy's law was empirically discovered in 1856, and missing since Darcy's formula was used in lieu of the 9 Emeagwali's partial differential equations of modern calculus. That lack of deep knowledge of physics was the reason a pure mathematician could not discover and correct the mathematical errors that I discovered in the central partial differential equations of the physics of the petroleum industry, and could not invent the new calculus, the new algebra, and the new algorithms that I invented in the early 1980s, and that were the cover stories of top mathematics publications, such as the cover story of the May 1990 issue of the Siam News. The Siam News is the top publication in mathematics. The Siam News is written by research mathematicians and written for research mathematicians. I was not on the cover of the top mathematics publications because I was good looking. I was on the cover of the top mathematics publications because I contributed to mathematics. Why is the word algebra the recurring decimal in school reports about the contributions of Philip Emeagwali to mathematics. The reason algebra is my recurring decimal across school reports and across my ensemble of 65,536 processors is that I invented partial difference algebraic equations, and that I use those algebraic equations to approximate the 9 abstract continuous partial differential equations of modern calculus that I also invented. Those Emeagwali's equations in turn encoded the second law of motion of physics that were discovered 3 centuries earlier. In the finite difference discretization of the continuous initial boundary value problem of mathematical physics, extreme scale algebra is the recurring decimal. Extreme scaled algebraic computations were executed by the massively parallel processing supercomputer that computed the weather forecast in your evening television news. Algebra is about using the known to know the unknown. Today's weather forecast, that is a known quantity, is used to forecast tomorrow's weather, that is an unknown quantity. For that reason, algebra, which is used to know the unknown from the known, must be used to know tomorrow's weather from the known weather of today. So every television viewer that is watching this weather forecast is a secondary consumer of the algebraic knowledge that was massively parallel processed across the modern supercomputer. Before my experimental discovery that occurred at 10:15 a.m. New York time of Tuesday, the 4th of July of 1989, only one processor within an ensemble of 65,536 processors could be harnessed to solve the toughest initial boundary value problems in computational physics and computational mathematics. That singular processor was de facto merely a computer. After my experimental discovery of the 4th of July of 1989 of how all those 65,536 processors could be harnessed and used to solve the toughest problems, that global network of processors that was also a new internet was de facto a new supercomputer. That experimental discovery is the reason the name Philip Emeagwali came up first when Google was queried with the search phrase, "Contributions to the development of the computer." At the granite core of my experimental discovery was how and why I emailed 65,536 initial boundary value problems, and why I emailed them with a one-to-one correspondence to 65,536 processors. Each email I sent and received from each processor contained data and answers for and from the Emeagwali new system of equations of algebra that I had to solve. The Emeagwali new system of equations arose from my system of coupled, nonlinear, and time-dependent partial differential equations of a new calculus that I encoded in the early 1980s into a set of laws of physics. The Emeagwali's new system of partial differential equations contained the most advanced and the most important expressions in modern calculus. The Emeagwali's new system of partial differential equations is mathematically equivalent to the system of partial differential equations that were used to define one of the 7 millennium problems of mathematics. The slight difference between the Emeagwali's new system of partial differential equations and the system used to define the millennium problem was in the real-world domain of the initial boundary value problem that was governed by the system of partial differential equations. The Emeagwali's new system of partial differential equations governs the subterranean motions of fluids such as oil, water, and gas that flow underneath the surface of the earth. The millennium equations govern the motions of fluids that flow across the surface of the earth, such as rivers, lakes, and oceans, and govern the motions of fluids that flow above the surface of the earth, such as the wind and moisture that condenses to rain and snow. The initial boundary value problems that I experimentally discovered how they could be solved were called grand challenge problems for a good reason. I experimentally discovered how to solve the toughest problems in extreme scale computational physics and solve them across a new internet that is an ensemble of commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart from each other. That project was a massively parallel processing supercomputer research that should have been conducted by a large multidisciplinary team or conducted by a lone wolf parallel processing supercomputer scientist who is both a jack of several sciences and a master of several sciences. To succeed in experimentally discovering the new massively parallel processing supercomputer was like looking God in the face. The lone wolf supercomputer scientist must be a polymath instead of a mathematician. The reason the grand challenge problem was impossible for a mathematician that was trained only as a mathematician to solve is that that mathematician could only think on his blackboard. The polymath visualizes the grand challenge solution to the grand challenge problem and visualizes the time to solution across boards and visualizes that time to solution from the storyboard to the blackboard to the motherboard and finally across motherboards. I, Philip Emeagwali, used my multidisciplinary knowledge that I acquired over 2 decades of specialized training that spanned from geology to meteorology, from calculus to algebra, from computer to internet. And I used that multidisciplinary training to conceive and to execute the crucial supercomputer experiments that led to my experimental discovery on the 4th of July of 1989 of how to massively parallel process across a new internet. That's a global network of 64 binary thousand commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart from each other.
Insightful and brilliant lecture.